Good evening. I will share the slides now. Hope the slides are visible. Good evening, all. Welcome to week 8 assignments. That is the last assignments of this course. For the course Introductory Organic Chemistry to August 2024 to October 2024 by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMRF TF for this course from IIT Bombay. So, coming to the summary of the week 8 modules, in week 8, rearrangement reactions and name reactions have been discussed. So, first, coming to neighboring group participation, so we can see that this compound with a pHs in it reacts 600 times faster than this normal alkyl chain chloride. So, what could be the reason? And coming to another example, here this either chloride having this either incorporated reacts with nucleophiles 10 power 6 times as fast as normal alkyl chloride. So what makes a difference in reactivity? So in this case, so the oxygen lone pairs can fall into this position, leading to formation of this oxonium type ion and removing this chloride. Then the incoming alcohol can attack at this position and neutralize the positive charge on this oxygen, leading to formation of this product. So here the lone pair on oxygen that is participating for the reaction to become more faster. So here a pi bonded cationic intermediate will be formed. And in our first case, the lone pair on the sulfur of this pHs can attack in an SN2 fashion at this center, and the Cl minus ion will be leaved and a three membered ring intermediate will be forming. Then the alcohol can attack either this position or this position, and it will lead to formation of the final product. So in both cases, the neighboring groups are participating, enhancing the reactivity and making the reaction more faster. Now coming to this example, and this is where we can come to know the rearrangement have taken place. So here this is a normal carbon atom and this is the labeled carbon atom with 14C label, and here this is our living group OTS, and this is the nucleophile. So here the phenonium ion will be forming. This will attack at this position and the OTS will be leaving, leading to formation of this phenonium ion. So here a positive charge will be formed. Then the RCO2H, it can attack either this position or this position. There is 50% possibility for both. So if it is attacking at this position, it will lead to formation of the rearranged product. And if it is attacking at this position, it will lead to formation of this unrearranged product. So here we can see how rearrangement is taking place. So if it is attacking at this position, we are getting the unrearranged product, and if it is attacking at this position, we will get the rearranged product. It will attack at this position and this will get neutralized. Positive charge will get neutralized. Now coming to Wagner-Mervin rearrangement, it is a carbocation rearrangement. So we are having this camphenyl, and when it is treated with H+, it will lead to formation of this xanthine. So what is happening here? There were two methyl groups at this position, and here there is only one methyl, and this alcohol is getting removed and the methyl is getting shifted here. So what is the mechanism that is taking place here? So we can see in the presence of acid, this OH will get protonated and this OH2 will leave, leading to formation of a carbocation intermediate. So this proton if it is getting lost, we will be getting this alkene which is not favored according to Brett's rule. So it is Brett's rule violation. Now the other possibility is, here there is no proton, so either one of the methyl groups will migrate. So one of the methyl group can migrate here, leading to formation of this tertiary carbocation. So the secondary carbocation is getting converted into a more stable tertiary carbocation, so that will be the driving force for this reaction. So here a proton is there that can get eliminated in an even elimination fashion, leading to formation of this alkene. So this is the mechanism for Wagner-Mervin rearrangement. Now coming to Demjanov rearrangement. So if we are having an amine, so when we are treating with HONO, it will lead to formation of this N2 plus, that is diazonium species. So here this is a better living group. So what will happen? Uh, this bond can break and it will migrate to this position, and this N2 will be removed, leading to formation of this cyclic carbocation. Now the water can come and attack at this position, and upon a deprotonation it will lead to formation of this alcohol. So here the amine is getting converted into an alcohol by ring expansion. This is Dimjanov rearrangement. Now coming to Beckmann rearrangement, here we are having this oxime. So in the presence of H2SO4, this will get protonated, leading to formation of OH2 plus. So what will happen? Alkyl migration can take place and the water will be removing. So here uh, the alkene that is trans to this OH2 will be migrating. So this will migrate to this nitrogen sender, and this OH2 will remove, leading to formation of this carbocation. Then the water can attack on this carbocation, leading to formation of this compound. And this upon tautomerization, it will lead to formation of the cyclic amide. So this is the mechanism for Beckmann rearrangement. So the rearrangement is taking place at this position. Now coming to Baker-Venkatraman rearrangement. So here we are having this species, and when it is treated with base, so here there is an alpha proton. That proton will be abstracted, leading to formation of an enolate at this position. Now once this O minus will fall here, this carbon-carbon double bond will go and attack on this carbonyl sender, leading to formation of this tetrahedral. Now this O minus will fall and this bond will break, leading to formation of this 1,3 dicarbonyl species. Okay, and this upon protonation it will give our desired product. So this is the mechanism for Baker-Venkatraman rearrangement. Now coming to Cartier's rearrangement. So we are having an acyl acide. This upon heating, N2 will be lost. So here we can see R double bond O, N minus. So now this N2 can lose, and here there will be a nitrine intermediate, and that this upon going here, this group can migrate to this nitrogen, and it will lead to formation of this isocyanate. And this is the intermediate in this reaction, and upon this isocyanate reacting with alcohol, it can lead to formation of this carbamate, and when it is reacting with water, it can lead to formation of carboxylic acid, and decarbonylation reaction carboxylation reaction will take place, leading to formation of amine, and when it will react with amine, it will lead to formation of urea. So this is the Cartier's rearrangement, and this is one of the rearrangement that involves an isocyanate intermediate. Now coming to Lawson rearrangement. So here we are having an hydroxamate ester. and in the presence of a base it is getting converted into an isocyanate. So here this is the hydroxamate ester. So in the presence of the base, this proton on this nitrogen will be more acidic, so that proton will get abstracted. Now this lone pair on nitrogen will fall here, and this R will migrate to nitrogen, and this carboxylate will be getting removed. So this will be getting removed, and we are getting this isocyanate intermediate. Now the water can attack on this carbon of the isocyanate, leading to formation of this acid, and this upon decarboxylation, in this fashion the proton will be abstracted, this bond will get broken, and this bond will get broken, leading to formation of an amine, and CO2 will be getting removed. So this is the mechanism for Lawson rearrangement. Here also this isocyanate intermediate is the common intermediate. Now coming to some name reactions that were discussed in this module. So Julia olefination reaction. So we are having the sulfone. So here this proton will be acidic, as it will be because of the presence of the sulfone at this position, it is electron withdrawing in nature. So that anion will be generated and it will add on to this. So in the presence of butyl lithium, this will lead to formation of this anion. It will add on to this aldehyde, and this O minus that will be generated will be reacting with this R3X, leading to formation of OR3. So this upon treating with sodium amalgam, it will lead to formation of this alkene. Now Peterson reaction, it is another reaction leading to formation of olefin. So we are having this beta hydroxy silyl compounds in the presence of NaH. So it will orient in such a fashion that the silyl and oxygen will come in the same position. So the NaH will be abstracting the proton of OH, and this will form this four membered transition state, and this upon breaking, it will lead to formation of this alkene. Now, Grignard reaction, we are all familiar about Grignard reaction. So, our MgX species will be adding to this carbonyl in a 1-2 fashion, and this tetrahedral intermediate will be formed, and this upon acidic workup, it will lead to formation of this tertiary alcohol. Okay. So, in this, they have shown like radical mechanism, just but it is just like normal addition reaction. Now Riemann reaction. So here chloroform is acting as a reagent. So chloroform in the presence of a base. So proton will be abstracted, and we will get the species. And this upon removal of one chlorine, we will get this dichlorocarbene. So that is acting as the reagent here. So the phenol, that proton will be abstracted by the base, and it can rearrange in this fashion. So here an anion will be generated that will attack on this carbene, and it will lead to formation of this species. And then what will happen, this CCl2 will be abstracting this proton here, and this proton will be abstracted, and then this aromaticity will be regained. So this is the most stable, as this is aromatic compared to this structure. Then what will happen, this upon removal of 2 chloride by OH minus, it will lead to formation of this aldehyde. So what we will tell this compound, ortho hydroxy benzaldehyde will be formed. Now while discussing problems, we will be coming through the other reactions that were discussed in this week, that is Pinacol rearrangement, Bayer vinegar rearrangement, benzylic acid rearrangement, dienone phenol rearrangement, Fries rearrangement, Schmidt rearrangement, Hoffman rearrangement, Wittig reaction, Shapiro reaction, Prevost reaction, Woodward reaction. These all reactions we will be discussing while we are solving the problems. So for reference, you can follow chapter 37 of Claydon Organic Chemistry for rearrangement reactions. So now coming to question number 1. Identify the major rearrangement product of the following reaction. So this is our compound, okay, and we are treating it with HCl, so acidic condition. So what will be the product that is getting formed? It is a sort of carbocation rearrangement. So what is the major product that is formed here? D is wrong answer. The correct answer will be option A. We will see how it is taking place. So here actually what is happening, this is a four membered system here. So while treating with HCl, the ring will expand leading to formation of the five membered ring. So this is the product that is getting formed. So this ring expansion is the driving force for this reaction. So here what will happen first, in the presence of HCl, the alkene that is present here will get protonated and we will get a tertiary carbocation. Okay. Now an alkyl migration will be taking place. This 1,4 bond will be breaking and 1,5 bond will be forming. So an alkyl migration will take place and a secondary carbocation will form. So here we can see the first we are having a tertiary carbocation and it is getting converted into a secondary carbocation which is less stable. But here the major driving force is that the congested or strained four-membered ring is converting into a five-membered ring which is much stable. So here this is acting as the driving force for this reaction. Now the chloride ion that will be present in the reaction medium will come and attack on this carbocation, leading to formation of the final product. Is the mechanism clear? Okay. So the final answer is option A. Now coming to second question. What is a major product formed in the following rearrangement reaction? So here we are having this ketone and it is treated with methyl Wittig reagent. So this ketone will be converted into an alkene. So this upon treating with osmium tetroxide, it will undergo dihydroxylation leading to formation of this compound. And when we will treat with tosyl chloride and pyridine, the primary alcohol will get tosylated and this product, the product that is forming here, it will undergo rearrangement. So what will be the final product? So here OH, OTS. This will be undergoing rearrangement. Any idea? C. Yeah. C will be the right answer. So here is semi-pinoculone type rearrangement is taking place. So once this lone pair on oxygen will fall here, this bond will break and it will migrate to this position and this OTS will get removed. So we will get this as the final product. So this is the mechanism. So upon treating with tosyl chloride pyridine, we will get selective tosylation of the primary alcohol and then When we treat with a mild base like CaCO3, maybe here they have forgotten to give that reagent. So then this lone pair on alcohol will shift here and this bond will break and it will shift, leading to elimination of tosyl, and we will get this ring expanded product. Mechanism is clear? Okay. So the final product is option C. Now coming to question number 3. In the reaction shown below, identify the correct combination of intermediate P and the final product Q. So seeing the reagent and the starting materials, can you guess what is the reaction that is taking place here?
Julia olefination.
No, no. It is Shapiro reaction. So we are having a hydrazone and we are treating with excess of butyl lithium. So sir have discussed this also in the lecture. So this is Shapiro reaction. So can you guess the products? That is intermediate P and the final product Q. Any guess? It will not be A. I will show the mechanism. So it will be more clear. So we are having this tosyl hydrazone. So here this this is acidic proton as it is attached to nitrogen as well as tosyl group, which will be more electron withdrawing in nature. So that proton will be abstracted, leading to formation of this intermediate. So here in the reaction condition it is mentioned we are using excess butyl lithium. So this alpha proton, it will be also acidic, so butyl lithium will abstract that proton as well, leading to formation of this intermediate. Then what will happen, this anion will undergo delocalization like this, and this bond will shift here and this tosyl group will get removed. Now this n minus, it can fall here and it will lead to formation of an anion here. So this lithium intermediate will be formed. So it will be like minus Li plus. Okay. Now this can attack on this aldehyde and lead to formation of this alcohol. So this is the intermediate P and this is the final product Q. So is it clear? First, most acidic proton will be this proton. That proton will get abstracted, leading to formation of this intermediate. Then we are using excess of butyl lithium. So this proton, this alpha proton can also be abstracted. Then upon delocalization, this tosyl group will get removed. And then this N minus, when it will come here, this N2 will get removed and an anion will be generating at the center. So Li plus, it can form like ionic bond, leading to formation of this compound P. So this is the intermediate. This intermediate can attack on this aldehyde, leading to formation of this alcohol, that is Q. So the right option will be option B. Is it clear? Okay. Now coming to question number 4. Identify the major product of the given reaction. So seeing the starting material and the reaction condition, can you guess what is the rearrangement?
Pinacol, pinacolon
Yeah,
rearrangement.
it is pinacol pinacolone rearrangement. So what is the major product that is formed here?
Option A.
Option A is a chance, but we have to take into consideration the migratory aptitude. So considering that migratory aptitude, option B will be the right answer. So coming to mechanism, so here there are two possibilities. Either this can get protonated or this can get protonated, right? So when this will get protonated, this OH2 will get removed and this carbocation will be formed. It is a tertiary carbocation, and then this phenyl group can migrate when the oxygen lone pairs are coming. So, but this product is not getting formed. What is the reason? Because when this OH is getting protonated and it is getting removed, this carbocation is formed. So here two benzyl, it is benzylic position of two phenyl groups. So this will be much more stable compared to the other carbocation that is getting formed. So that is why this will be formed as major, and then this lone pair will fall here and this 1,2 bond will break and it will lead to formation of this 2,6 bond. So we will get this as the final product. Okay, this is the reason. The benzylic cation is more stable and is formed faster. So this will lead to formation of this major product. So option B will be the right answer. Is this clear? Okay. Now coming to question number 5. What is the major rearrangement product of the following reaction? So seeing this starting material and reaction condition, can you guess what is the rearrangement?
Dinon-phenol
Yeah,
rearrangement.
you are correct. It is dienone phenol rearrangement. So what is the product?
Option C.
It will be option A. Okay, because in option C an extra alkene is coming. That is not here. So this is the mechanism. We are having this dienone. So this will get protonated in the presence of an acid. Now this bond can migrate to this position and this bond will shift here and this positive charge on oxygen will get neutralized. So we will be getting this intermediate. Then this proton will get removed, leading to aromaticity. So this will be the final product that is getting formed. Clear? Okay. So option A is the right answer. Now coming to question number 6. The correct statement about the following reaction is. So we are having an amide. It is treated with Br2 NaOH So what is the rearrangement that is taking place here?
Hoffman rearrangement.
Yeah, it is Hoffman rearrangement. So based on this, what will be the right statement? The product is 2-fluoropyridine 3-amine and the reaction involves nitrene intermediate. The product is 2-fluoropyridine 3-amine. That is the structure will be like this. And the reaction involves radical intermediate. Then the product is 2-hydroxy nicotinamide and the reaction involves benzene like intermediate. The product is 2-hydroxy nicotinamide and the reaction involves addition elimination mechanism. So we know if it is Hoffman rearrangement, we should get this as a final product. Okay. So we can rule out these two options. Then out of these two, what is the right one?
Option A.
Option A is the right answer. So we can see the mechanism. So in Hoffman rearrangement, in the presence of an base, this proton is acidic proton. It will be abstracted and this enolate sort of intermediate will form. This upon falling. So here the nitrene is forming. Okay, N minus. Then this upon falling here, this C double bond N can abstract the bromine, and this bromide will be leaving. So then again OH minus will abstract the proton. Then this enolate sort of intermediate will be forming. And once this is falling back here, this bond will shift to this group will shift to nitrogen and bromide will lose. So here an isocyanate is getting formed. Okay. Now OH can add on to this carbon and it will lead to formation of this intermediate. Okay. Then decarboxylation reaction can take place. That is, this proton will be abstracted, the CO2 will get removed, and an amine is getting formed. So this is the mechanism for Hoffman rearrangement. Clear? So option A will be the right answer. So we will get 2-fluoropyridine 3-amine, 2-fluoropyridine 3-amine, and this reaction is involving an nitrene intermediate. Clear, right? Okay. Now coming to question number 7. Osmium tetroxide mediated dihydroxylation of the following compounds lead to formation of the following diols as exclusive products. So in the first reaction, osmium tetroxide treatment will lead to formation of this syn diol, and in the second reaction osmium tetroxide treatment will lead to formation of this syn diol. Okay. So here the options given are as shown above. In reaction A, the approach from top phase is preferred. As shown above, in reaction B, the approach from bottom phase is preferred. The methyl group hinders the approach in B and a reversal in facial selectivity is seen. All the above. So what is the correct statement? D. All of the above is the correct statement. So we know that osmium tetroxide dihydroxylation will lead to formation of syn alcohols. So in the first case, it is giving the stop phase preference. In the second case, since these two geminal dimethyl groups are there, it will cause hindrance and the osmium tetroxide attack will take place from the bottom phase, leading to formation of the product. So because of that, all these three statements are right. So option 4 will be the right answer. So this is the mechanism for osmium tetroxide reaction. So this is the structure of osmium tetroxide. So with alkene, it will form this 5 membered like transition state, and it will form this osmate ester. Then upon hydrolysis, it will form this diol, that is syn diol, and this compound. So we will be using NMO, N-methyl morpholine N oxide, so that will reoxidize this compound into osmium tetroxide. So in this reaction, we need osmium tetroxide only in catalytic amount, because NMO, it will regenerate osmium tetroxide back from this diol. Okay, so option 4 is the right answer. Any doubts?
Ma'am, what is NMO?
N-methyl morpholine N oxide.
Okay.
I will draw the structure like this. Okay, here one CH3 will also be there. N-methyl it is there, na? N-methyl morpholine N oxide. Now coming to question number 8. So here, identify the correct intermediate through which the Wittig reaction proceeds. So here we are given this ylide and this ketone, and it is leading to formation of this product, alkene. So they have mentioned it is Wittig reaction. So what is the intermediate for this reaction?
Option B.
Option B is the right answer. So we will get this 4 membered intermediate. So how it is taking place? So the light will be having a negative charge that will add on to this carbonyl carbon, and O minus will be resulted. Now this is having a negative charge and this is having a positive charge. So it will form a bond. Okay, ionic bond sort of. Now PPH3 O formation will be more favored. Phosphorus and oxygen bond will be more stronger. So this bond will cleave in this fashion, leading to formation of alkene, and PPH3O will be the byproduct. Clear? So this is our intermediate. Clear mechanism? Okay. Option B will be the right answer. Now coming to question number 9. The major product expected when 2s, 3s, 2,3-dimethyl cyclohexanone is treated with MCPBA, that is metachloroperbenzoic acid. So what is the major product formed and what is this rearrangement called? So this is Beyer-Villiger rearrangement. So what will be the right answer? Option B. Yeah. So here in Beyer-Villiger rearrangement, this is MCPBA, metachloroperbenzoic acid. So this lone pair on oxygen will add on to this carbonyl carbon and O minus will be resulted. And once this O minus will fall, then this bond will be migrating. So there are two ways. This bond can migrate or this bond can migrate. So here this bond is getting migrated and we will be getting this as the major product. That is what is the reason behind that. Here we will be having a here the carbocation that will be resulted will be secondary sort of, and here primary sort of. Okay, so the secondary will be more favored for migration compared to that of the primary, so we are getting this as a major product. So here option B is the right answer. Clear? Okay, now coming to question number 10. What will be X and Y in the following reaction? So here we are given an alkene and it is subjected for Prevost condition. Prevost and Woodward are dihydroxylation reactions. So here under Prevost condition it is giving X and under Woodward condition it is giving Y. So in this is dihydroxylation reaction. So there is a small difference between Prevost condition and Woodward condition. So according to that, X and Y will vary. So what is X, what is Y?
Option B.
Option B will be the right answer. So in Prevost condition, we will be getting anti-alcohols, and in a Woodward condition, we will get syndiols. Okay, here antidiol and here syndiol or transdiol, syndiol. So this is Prevost condition. So here in Prevost condition, we will use this silver benzoate and I2. So here this alkene will form iodinium ion with this uh, iodine. Then this benzoate it can attack on this position and it will open up this iodine. So here the attack will be in SN2 fashion. So we will be getting this product intermediate 4. Now this iodine it can coordinate with Ag plus. So this bond will be little labile. So this oxygen it can attack at this position and AgI will get removed, leading to formation of this intermediate 5. Then this another molecule of benzoate it will add at this position and this bond will get open, leading to formation of this compound 6, and this upon hydrolysis, ester hydrolysis lead to formation of transdiols. So this is Prevost reaction condition. Okay, is this mechanism clear? Okay, now instead of this benzoate we are using acetate in case of Woodward condition. So this Woodward reaction is just a modification of this Prevost reaction. So here the iodine will form iodonium ion by reacting with this alkene. So here we are having silver acetate. So the CH3COO minus will come and attack in SN2 fashion and this bond will open up. So here this intermediate will be forming. Now again this AgI bond will formation will be more feasible as silver have affinity towards halogens. Then this oxygen lone pairs can attack in an SN2 fashion here, and this AgI will get removed and we will get this intermediate. Now what will happen? Water will add on to this carbon, and it will lead to formation of this is orthoester sort of system. Okay, now what will happen? Now this can open up in this fashion. So this mono acetylated diol, it upon hydrolysis lead to formation of cis diol. So here both of this are in cis fashion. Both of this are coming in cis fashion, and it is leading to formation of this cis diol. Here it will again undergo hydrolysis. So OH2 I will write, then it will be more clear. It can undergo hydrolysis and it will lead to formation of cis diol. So this is the Woodward reaction mechanism. So just the difference between Prevost reaction and Woodward reaction is that in Woodward reaction we are using silver acetate, and in Prevost reaction we are using silver benzoate. So here in Prevost reaction we will get trans diol will be the product, and in Woodward reaction cis diol will be the product. Clear?
Ma'am, as in Prevost reaction, benzoate ion is attacking as nucleophile.
Hmm.
Why in this reaction acetate ion is not attacking as a nucleophile on the carbonyl carbon?
Means here,
Yeah, here. Why water is attacking? We are also having acetate ion.
yeah, maybe reactivity is lesser compared to that of water. I'm not exactly clear. I will check into it and tell in the summary tutorial. Okay.
Okay, ma'am.
So here option B is the right answer. In Prevost reaction, we will be getting trans diol, and in Woodward condition, we will be getting cis diol. Now coming to question number 11. Here we are having this ketone and it is treated with acid. So what will be the product that is formed here? It's sort of carbocation rearrangement only. I will number this A, B, C, D. What will be the product? It will be different. I will show you the mechanism. It is not A. So here we are having this ketone. Upon treating with acid, the ketone oxygen will get protonated. Now what will happen? This will get migrated to this position. This four-membered ring will open up and it will migrate to this position, neutralizing the positive charge on oxygen. So here now a new carbocation will be formed at the center. Since this bond is getting migrated, here a positive charge will generate. Now this hydroxyl lone pair on oxygen will fall here. So here this bond will be breaking and it will migrate to this position so as to neutralize the positive charge. So this will be a spiroketone that we will be getting. Mechanism clear? Okay. So the answer will be option D. So whenever there is chance for strain release and all, then that will be favored. So here there was a four-membered ring. So in this condition, the strain release was possible by expanding to a five-membered ring. So the reaction is moving forward in that direction. Now coming to question number 12. Identify the major rearrangement product formed in the following reaction. So what is this rearrangement or reaction?
Fries rearrangement.
Yeah. So this is Fry's rearrangement. So what is the major product that is formed here? So we have seen in the lecture that there is possibility for formation of both ortho and para products. So but one condition is that at lower temperatures, that is temperature less than 160 degrees Celsius, para product will be the major product. Para will be major and greater than 160 it will be ortho product that is major. Okay. So here it is 90 degree. Sorry. So here it is. Excuse me 1 second. 90 degrees Celsius. So the major product formed will be para 1. Okay. So option A will be the right answer. So just to keep in mind at lower temperatures, para product is favored. At higher temperature, ortho product will be favored. This reaction is like this is because delta H for para product is less. That is why at lower temperature it is getting formed, and at higher temperature delta H for ortho will be more. That is why at higher temperature we will be getting ortho product as major product. Okay. So this is the mechanism for Fry's rearrangement. So in the presence of AlCl3, AlCl3 can coordinate with this oxygen. Then this sorry this will fall here, and this positive charge on oxygen will be neutralized. So we will get acylium ion. Now this bond can break and this bond can shift in this fashion, and it can attack from the para position to this carbon, and this positive charge will get neutralized, leading to formation of this intermediate. Now this proton can get removed, leading to formation regaining of aromaticity. So this proton will be abstracted, it will shift in this fashion. Then this oxygen will abstract a proton, leading to formation of this para hydroxy compound. Okay. If we are getting ortho product, the mechanism will be like the attack will take place from this position. So option A will be the right answer. We will be getting para product as the major product. Mechanism clear? Okay. Now coming to question number 13. The given reaction leads to formation of. So here we are having a ketone. It is treated with a H2O2, hydrogen peroxide in acetic acid. So what will be the major product that we are getting? So here what is the rearrangement that can take place? As we have seen with MCPBA, which is also a paracid, here the Bayer vinegar rearrangement will be taking place. Okay. So what will be the product that is formed here? A, B, C, D. Ring expansion will be there. Okay. So C will be the right answer. We will see the mechanism. So this is our ketone. In H2O2 acetic acid, it will get protonated. Then H2O2, it can add on to this carbonyl and lead to formation of an alcohol. So this will be the intermediate. Now what will happen? Proton transfer can take place and this OH2 can form. Now this OH, this lone pair on oxygen will fold, and there are two possibility, either this bond can migrate or this bond can migrate. Since here the carbocation that will be formed as secondary and here primary, this migration will be favored. So this bond will get migrated here and the OH2 will get removed. So then it will result in the formation of this lactone. Okay, because whatever was here present already, 1, 2, 3, 4, and this oxygen that will be forming, it will be 5. Okay, so this 1,4 bond will break and it will lead to formation of 1,5 bond. 1, 2, 3, 4, 5. 1,5 bond will be formed. 1,4 broken, 1,5 formed. So a 5-membered ring is forming here. So this is the migratory aptitude. The substituents which can stabilize the positive charge can migrate readily. The migratory aptitude order in Beyer-Williger oxidation for various substituents is hydrogen. It can migrate at faster rate than tertiary alkyl, then cyclohexyl, then secondary alkyl, benzyl, aryl, primary alkyl, methyl. Okay. So here, because of that, this group will be migrating at a faster rate compared to this. 3,4 bond is not getting broken as it is primary alkyl. Here, this 1,4 bond is getting broken as it is a secondary alkyl that will be migrating. So the final product we are getting is option C. Is it clear?
Yes, ma'am.
Okay. Now coming to question number 14. So saying this, what is the rearrangement that is taking place here? We can see the mechanism. What can be the product?
Benzylic acid rearrangement.
Yeah, we will see the mechanism. This is benzylic acid rearrangement. So we are having this as a starting compound. And here, since this NH2, it can by resonance um, like interact with this carbonyl. So here this will be less electrophilic carbonyl. The more electrophilic carbonyl will be this one, okay? Because of this resonance from NH2. So this will be the more electrophilic carbonyl. So the OH will be attacking on this carbonyl carbon and this O minus will be getting formed. So this is our tetrahedral intermediate. Now what will happen once when this O minus will fall back, this phenyl group will migrate to this carbonyl and this O minus will form, leading to formation of this compound. Now proton transfer can take place from this OH to this O minus, leading to formation of this like this, okay? Then it can protonate and we will get the final acid. Clear? This is benzylic acid rearrangement. Mechanism clear? Why it is attacking on this carbonyl and not this carbonyl? Okay. So the product that we are getting is option A. Now coming to the last question of today's session. So here, predict the final product of the following rearrangement reaction. So here we are having a benzoic acid and it is treated with HN3. So it will undergo a rearrangement. So what is this? What is the name of this rearrangement reaction? So it is not necessary to remember the names of the reaction until unless we should know the mechanism. What is happening there? No, no, it is not Fry's rearrangement. So we will see the mechanism. So it is Schmidt rearrangement. In Schmidt rearrangement, carboxylic acid and its derivatives will be converted to amine and its derivatives. So we are having a carboxylic acid here and it is getting converted to an amine with here this CO2 removal is taking place. So one carbon will be less. So the carboxylic acid in the presence of HN3. So first this will get protonated, the presence of H plus. Then this lone pair on oxygen will fall and this water will get removed. We will get this acylium ion and this HN3 it can attack on this, leading to formation of this. This is our key starting material. Now what will happen, this N2 can leave and here a negative charge will be formed, and that when it is shifting here this bond will migrate to nitrogen and an isocyanate intermediate will be formed. Isocyanate. Now water can add on to this carbon of this isocyanate and we will get this acid. Now, what will happen? Decarboxylation will take place like this, and then amine will be formed as the final product. So, this is Schmidt the rearrangement. So, the final product we will be getting is option A. Clear? So, there
Yes,
are
ma'am.
many reactions involving this isocyanate intermediate. So, just have an idea like what is happening there, what is the mechanism that is taking place here. Once isocyanate is formed, then everything will be known, but how the isocyanate is forming, that is what you have to learn. Okay. So if there are no further doubts, we can wind up today's session. Thank you for joining, and next week on October 19th we will be having a summary tutorial where we will be discussing questions based on all the week's modules. Okay, thank you.
Thank you, ma'am.